Alright, well, hello again, and welcome to the third lecture in this course about physics. So last time we talked about Newton's first law of motion, having to do with inertia, how objects want to either, if they're at rest, they want to remain at rest. If they're in a uniform state of motion, meaning moving in a straight line at a constant speed, then they want to keep doing that as well. Right? And to stop them from doing that or to change their motion, a force needs to act on them. More specifically, there needs to be a net force that acts on an object in order to change its motion, its state of motion. So before we get into Newton's second law, we need to talk a little bit more about what's called linear motion. This is essentially motion in a straight line, right? Like zooming down the highway 60 miles an hour west, or falling straight downward, like dropping something. Right? So linear motion is not necessarily uniform motion, because as in the case where something is falling downward, it's actually speeding up as it falls down. Gravity is acting force on it, so it's constantly accelerating, it's increasing its speed. So that's not uniform motion, but it's linear motion, meaning it's just in a line. Yep. Okay. And before we say anything about linear motion in particular, it's worth mentioning that all motion is relative. Meaning, if I say that that car is driving 60 miles an hour down the highway, going west down the highway, I've told you it's motion, but what I haven't said and what's implied is that's relative to the Earth's surface, right? So I'm saying in that case that the Earth's surface is essentially at rest, then I can say, yeah, the car is moving with respect to the Earth's surface, this is the way the car is moving. Okay? But all motion, technically, you need to refer to a certain, what we call frame of reference. And you don't need to worry too much about that now, but it will come back in a big way at the very end of this course. So yeah, so to say that you're at rest right now is, yeah, with respect to the Earth's surface, you're at rest. However, the Earth's surface is rotating around, right? The Earth rotates on its axis, and it's actually rotating around very quickly. So you're actually in motion in that sense. And then beyond that, the Earth is actually orbiting around the Sun, and it's orbiting around the Sun incredibly quickly. Right? It goes a great distance in 1 year. So all that is just to emphasize that when you are describing motion, it's always implicitly, at least, with respect to something. Generally, that thing is the Earth's surface when we're talking about motion. So yeah, so we're not going to worry about that too much. It just needs to be pointed out, and for the most part, going forward, you just kind of assume that the motion that you describe is, again, with respect to the Earth's surface. So the Earth's surface is at rest, we're saying how things move relative to that. Okay, so bringing this back from the first lecture, where these are examples of proportional relationships, when we talk about the speed of an object, you're saying how quickly that object is moving, right? What's the rate of its motion? And the speed of an object, as we pointed out before, is proportional to the distance that object travels, and it is inversely proportional to the time that it takes to travel that distance. So if you're going a certain distance and it takes you an hour, and then you go a much further distance in that same hour, then greater distance traveled, greater speed. If, on the other hand, you're going a certain distance and it takes you, or if you're going a certain distance and it takes you an hour, and then you go that same distance and it takes you 2 hours, greater time to travel that distance, inversely proportional speed, that means you were going slower. Right? So greater time to travel, slower speed. So proportional relationship, inversely proportional relationship. And in fact, we define speed as just these two things. Right? So speed is explicitly the distance an object travels divided by the time that it took to travel that distance, or the time elapsed as it traveled that distance. So, for instance, if you say a car, or probably a car, is traveling 30 miles an hour, what you're really saying is that if it travels for an hour, or another way of saying what you're saying, is if it were to travel for an hour at that speed, it will go 30 miles. Or you could also say if it travels for an hour at that speed, it will have gone 30 miles. Or if it goes 30 miles at that speed, it will have taken an hour. Right? All those things are ways of saying that its speed is 30 miles per hour. So we indicate speed as a distance over a time measurement. So when we're talking about 30 miles per hour, another way of writing that would be 30 essentially miles divided by hours. Okay, so if you take that definition of speed, then we can pretty simply rearrange that equation, or that relationship, by essentially multiplying both sides by this time elapsed. And we end up getting this relationship, which says that the distance an object travels is equal to its speed multiplied by the time that elapsed for it to travel that distance. So we wrote a big X in there for multiplication, but sometimes when I show you guys equations, if it's just these things in parentheses next to each other, hopefully you know that implies multiplication. So as an example, if an object is, or the speed of an object, maybe a car, is 30 miles per hour again, and it travels for 2 hours, then 30 miles an hour at speed multiplied by 2 hours, the time elapsed equals 60 miles that it traveled. And this is more of like a warning that's not really going to, you don't have to worry about so much in this class, and for the reason that this isn't a class about units. Units are something like, mile as a unit, a newton we talked about before was a unit, right? It's ways of measuring things. And those things are very important in their own sense, and they can be extremely useful, but for our case, I don't really feel it's much of a use for you to worry about what the unit of something is. As long as you know we're talking about a speed, then it's a speed. It's like a miles per hour or meters per second. But I don't really care exactly what the units are as long as I know that it's a speed, right? The only warning here really is if you, more than doing a calculation, is if you're comparing two things together or comparing things against each other. If I say, what's faster, 60 miles per hour or 60 meters per second, I don't expect you to know the answer, but I expect you to say, well, I don't know that right away because they're not the same units. Right? Like the same idea as if, which is longer, a meter or 3 feet? Well, if you don't know how they're related to each other, then that's all there is. I just don't know. Right? Turns out a meter is a little bit longer than 3 feet, so the meter's longer. Yeah. Okay. So, as just a little check on yourself here, go ahead and try to answer these questions about the average speed of a cheetah in these two different instances, and how far a car will travel if it's going at a certain speed. And this one does have to do with that unit sort of thing in the last one. So, yeah. So go ahead and pause and take a crack at it. Okay, so for that first question, and in the first part of that, if the cheetah's gone 100 meters in 4 seconds, and that's the distance it traveled and the time that elapsed as it traveled, right? 100 meters divided by 4 seconds, 25 meters per second is the technical unit. And more compactly, you can write meters per second as just m divided by s. What if it goes 50 meters in 2 seconds? Well, that's the distance it traveled, that's the time that elapsed when it traveled that distance. 50 meters divided by 2 seconds, what do you know? It's still 25 meters per second, right? So even though you have different measurements, it could still be the same speed that you're actually measuring. And then in this case, the second question, calculating how far something went, the only real questionable part of this is that, well, we're given a speed, or I gave you a speed in kilometers per hour, but told you amount of time in minutes. So the first step is really just to say, well, I can't use kilometers per hour and minutes together. I need kilometers per hour and hours together. So if 60 minutes is 1 hour, great. Multiply that speed by that time. The object or the car went 100 kilometers. So something kind of glossed over here, good time to talk about now, is whether or not when we're talking about things like speed, or other stuff later on, whether we're meaning an average speed versus an instantaneous speed. So in all the cases in the past couple slides where it was like, okay, you went this far and it took this amount of time, so just divide those things, that tells you your speed. Right? What that is actually telling you is the average speed. Right? So on average, if you say, if it took you an hour to go 25 miles, then on average your speed was that distance, 25 miles divided by 1 hour, 25 miles per hour. However, that's different than your instantaneous speed. And instantaneous is just another word for what's your speed at that moment, at that instant. Right? So, like if your average speed was 25 miles an hour, you could have been going faster than 25 miles per hour, you could have been going slower than 25 miles per hour, right? But on average, all that sort of evened out to be 25 miles per hour. Yeah. So, if you're on a trip, or if you're going this 25 miles an hour, or 25 miles, and it takes you an hour, your instantaneous speed might be all kinds of different things. It's going to be 0 at times when you're at a stop sign or a stoplight. Maybe it's 60 miles an hour when you're on the highway for a few minutes. Yeah, so instant versus like just averaging over the entire trip. Yeah. All right, so another question then. If your car, say, has an average speed of 60 miles per hour, you want to trip your car at, you went on an average speed of, your average speed is 60 miles per hour. So is it possible for the instantaneous speed of your car to be less than 60 miles per hour? And then beyond that, is it possible for the instantaneous speed to always be less than 60 miles per hour? So go ahead and pause the video and think about it, write out an answer. It doesn't have to be long, just a couple words, yes, no, whatever you want. Okay, so hopefully you answered yes to the first question, because I kind of said that in the last slide. But as far as the second question goes, can your instantaneous speed always be less than 60 miles per hour? The answer is no, because if you always have an amount that's less than 60 miles per hour, it's never going to average out to be greater than all those instantaneous moments. Right? So if you're always traveling at 25 miles per hour, there's no way that on average you're going to get 60 miles per hour. Right? Yeah. So if you're traveling slower than 60 miles per hour and instantaneously at some times during the trip, that for your speed to average out to 60 miles per hour, that means you have to have traveled faster than 60 miles per hour at some points too. All right. So all that was about speed, right? Speed is just how the rate that an object is moving, right? Distance and time. Yeah. In physics, turns out that, not just in physics, but beyond the topic or the term of speed, there's something else which we call velocity. Right? So speed, or velocity, is essentially speed with direction. And if I say that I'm driving 60 miles an hour down the highway, well, okay, you've given me a speed, but you really haven't told me a direction. If I say 60 miles per hour north on the highway, then I have a speed, I have a direction, I know the velocity, the full velocity of that car. Right? So this is again indicating another quantity that is a vector quantity. Right? So velocity is a vector quantity. It has a speed, or it has an amount the speed, and has a direction. Right? So all these are examples. 30 miles per hour northward, 25 meters per second downward. And if you draw a picture of an object, then you can indicate its velocity with an arrow, and generally you draw or you write next to it its speed, the amount that that vector is indicating. Right? So like in this top one, it's like you have this sort of rocker or something like that, and it's moving its 25 meters per second upward. The arrow is indicating the upward direction. The length is sort of indicative of its amount of velocity or its speed. Right? A much larger arrow would indicate a much larger speed, but it's still in the same direction. So that would be 25 miles per hour upward, the arrow's going upward. This is 25 miles per hour downward, right? Another rock. So these two rocks actually have the same speed. They're both moving at 25 meters per second, but they have different velocities. And that is because the directions are different that they're moving. And even if I just took this top one, or this bottom one, and you just tilted that angle just a little bit, it's not quite upward, it's off of being upward just a tiny bit, it's a different velocity, right? It's not exactly upward, so it's not the same velocity anymore. So in order for two things to have the same velocity, or for the velocity of an object to remain unchanged, its speed needs to be constant and the direction it's moving needs to be constant. All right, so more questions for you. If the speedometer of your car, I guess you're not in America somewhere because it's in kilometers per hour, but if the speedometer of your car is, when you're moving east, reads 100 kilometers per hour, and you pass another car that's moving west at 100 kilometers per hour, do you have the same speed and do you have the same velocity? And then in a separate question, if during a certain period of time the speedometer of your car shows a constant 60 kilometers per hour, does that indicate a constant speed? And does that also indicate a constant velocity? So again, pause and write down your answers for each of these. All right. So, yeah, for the first one, both of the cars are moving at 100 kilometers per hour. Those are the speeds of the cars, right? So the speeds are the same. The velocities, however, are different because the cars are moving in opposite directions. Right? So 100 kilometers per hour east and 100 kilometers per hour west, different directions, different velocities. And if your car was showing a constant 60 kilometers per hour on the speedometer, then indeed that's a constant speed. Right? 60 kilometers per hour is just staying constant. Doesn't really care about direction moving. Is it a constant velocity? Well, that's a little bit trickier. It could be. This is somewhat of a trick question because the answer is I don't know. It could be, but it could not be. Right? So it would be a constant velocity if that car was going 60 miles per hour and just continuing straight along in the same direction. However, if that car ever has to turn or go in a bit of a different direction, then its velocity is no longer constant, right? Because as long as it's not moving in the exact same direction, if it goes off even a little bit, its velocity has changed. Right? Different direction, different velocity. So I guess maybe the better answer is it's could be a constant velocity, but probably not. Usually you're not going exactly straight all the time. Okay, so look. Okay, so now that we know a little bit about velocity, how does velocity change, or what happens when velocity changes? Well, since velocity is made up of speed and direction, if you want to change an object's velocity, you can change its speed, or you can change its direction, or you can change both. Right? But you need to at least change one of those things, and if either of those things changes, or both of them change, then the velocity of that object has changed. Right? So on the left side here, we have an object that's falling, and up at this height, maybe it's moving at 10 meters per second, and it's moving downward. A little bit later on, it's still moving downward, it's moving in the same direction, but it's now moving at 25 meters per second, so its speed has changed. Its speed has actually increased here. So that is an example of velocity changing, and not because the direction changed, but because the actual speed of the object changed. So the other great example of changing an object velocity is where its direction changes, but its speed does not. So if on the right side here we look at the same sort of object, it's moving at 25 meters per second in that upward, up to the right sort of path, and then later on we see it's moving 25 meters per second in that down to the right path. Its speed has remained the same. It's still 25 meters per second. However, its direction has changed. It's gone from going in this direction now to going in this direction. So it's turned in some way. And this is another way you can change velocity. So this gets into actually curved motion or rotational motion, and that's not technically linear motion because it's not a straight line anymore. So we're not going to touch much more about that here, but that will come back later on. We talk about rotations and curved paths later on. Different lectures. Alright, so what is it called when you change an object's velocity? Well, that is an acceleration. Right? Acceleration is exactly changing an object's velocity. An object. Technically, the definition of acceleration is the change in that object's velocity divided by the time that it took to change that velocity. And I guess specifically this is only for the magnitude or the amount that the acceleration changes. Right? So this we also have to keep in mind that if the direction of that velocity changed, then that's a way to change the velocity. So not just a changing speed, but also could be changing direction. Okay. So anytime an object's velocity changes, it's accelerating in some way. So examples of things accelerating are when an object speeds up, right? Its speed increases, its velocity has changed, it's accelerated. When an object slows down, its speed is decreased, right? Its velocity has decreased, it's accelerated. When an object turns, changes direction, right? Its speed has stayed the same, but its direction has changed, so it's also accelerated. And a good example of an accelerating object is just an object in free fall, when we just release an object and it gets pulled down to the Earth's surface. Alright, so since free fall or dropping an object is a good example of acceleration, we're going to look into that for the next few slides at least. So what happens when you release an object? Right? Well, I've kind of just told you, I've given away the fact that it's going to accelerate. Gravity is acting a force on that object to pull it downward, and that force accelerates it downward. Okay? So if you have an object and you just release it, it starts out at rest, right? It has zero velocity, there's zero speed, so it's not moving in any direction. But once I release it, it starts to move downward. And not only does it just start to move downward, it's moving downward faster and faster and faster and faster. That's the idea of acceleration. The direction that it's moving is constant, but the velocity is changing because its speed is increasing. So it starts from not zero speed, release it, up to a meter per second, up to 2 meters per second, up to 5 meters per second, up to 10 meters per second, right? And it increases in that way. So an example or a way of seeing, or not even seeing, of actually hearing this process in action is if you take a string of balls, or I'm actually going to use some metal clips here, but if you string them out and you string them at even intervals, so I don't know exactly what the interval is on this one, but it's about 1.5 feet maybe in between each of these. So the distance between each of these clips is the same. So if you think about it for a second, when I release them, you might imagine that they just move at the same speed. And if they did move at the same speed, then what would you hear as they hit the ground? Right? If they're moving at the same speed, then since they're at even intervals, at even distances here, they're going to hit the ground in even time intervals too. And you just hear this click, 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 click. It's not going to change. It'll be a consistent kind of clicking noise, right, or tapping noise. However, since they are accelerating, they're not actually moving at a constant velocity. What you do here, or what you would expect to hear with the acceleration, is you hear a shorter and shorter time interval as these objects drop, right? Because the first one's going to hit the ground. The second one is going to have sped up and moved a bit faster. It's going to hit the ground behind it. The third one is going to be even moving faster than that second one. So it's going to take even less time before it hits the ground after the second one. Same thing with the fourth one. It's going to take even less time than the third one did to the second one. And finally the top one is going to take even less time, right? So what we would expect to hear if they're accelerating is this click, 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 okay? So we're going to try it. I hope you can hear it over the speaker. I don't know, maybe you can, maybe you can't. Let's see. Ooh. And now it's a tangled mess. Okay, well, if you, hopefully the speaker picked that up, but if not, you're just going to have to take my word for it. The first click is like the bottom one hitting the ground, and the second one hitting the ground is like click, click, and then the frequency or the time interval in between those clicks just gets smaller and smaller and smaller. And that's because the ones at the top have had a longer time to fall. They've been accelerated more, so they're moving faster and faster and faster, and they cover that same distance in less time. Okay, so let's look at that in more detail. Okay. Not thinking this isn't a string of balls, this is the same sort of object now. We're imagining I just released a single object. Okay. So how fast do those objects fall? Well, I've told you that they accelerate, so the speed that they're falling is actually increasing as they fall further and further. And they're accelerating under gravity. So this is the first instance where we'll tell you, and this will come back many different times, that the acceleration due to gravity on the Earth's surface is approximately pretty close to 10 meters per second every second. What that means is that in 1 second, the object's velocity will have increased by 10 meters per second. So if you release, say, like release this ball, in 1 second we will have gone from rest, 0 velocity, 0 speed, to, in 1 second, to 10 meters per second. In the next second, it will have increased its velocity another 10 meters per second. So after 2 seconds, it now will be moving at 20 meters per second. After 3 seconds, it will increase its velocity again, because it's been continually being accelerated, to now 30 meters per second. So this is what it is meant by an acceleration of 10 meters per second every second, or 10 meters per second per second. So every second you increase this object's velocity by 10 meters per second. So this is also why the longer an object is falling, the greater distance it's going to travel in each second. It's the same idea of why when I release those things, that string of clips, that the higher clips had longer to fall, so they gained more speed, their speed had increased more, and it was a smaller time interval as they hit the ground. So another interesting thing is that the fact that gravity is accelerating objects downward at 10 meters per second means that this same sort of motion occurs whether you're whether it's slowing an object down, whether it's decelerating an object, and it will decelerate an object if you say toss it upward. Right? So if you give an object some just toss an object up, you'll give it some speed, so it'll be moving, when it leaves your hand, it's moving at some velocity, right? But again, gravity's still trying to accelerate it downward, so in this case, acceleration is acting against the motion of the object, and we call that deceleration. So you toss the object up, gravity decelerates it, so 10 meters per second every second. So here in this picture, if you imagine on like the blue arrow side, if I toss that object up at 30 meters per second, right? That's the velocity it leaves my hand with. Then after 1 second, gravity will have decelerated it, decelerated by 10 meters per second. So after 1 second, it's now only moving at 20 meters per second upward. 1 more second later, it will have decelerated again by 10 meters per second. So now it's only moving at 10 meters per second. And then finally 1 second more after that, it will have decelerated again by 10 meters per second. So now it's not moving at all. It's at zero velocity right up here, and that's where it's reached its peak, and it's going to start to then move downward now, right? Because again, that acceleration due to gravity never stops, right? It's decelerating it, decelerating it, decelerating it, and now it's accelerating it once it starts to move back in the other direction. So this motion actually is sort of a mirror image. It's symmetric. When you toss the object up, it decelerates, and then it accelerates in the exact same way on the, exact same way, but sort of in reverse, I guess, on the way down. So you get this same sort of picture when you toss the object up as when it falls back down. All right, so that's looking at, say, how fast the objects are moving due to that acceleration of gravity. What about how far they fall? So if you want to know how far an object has traveled, well, if it had a constant velocity, or it had a constant speed even, then it's pretty easy to tell how far it went, right? You just multiply speed by the time that it was traveling that speed, and you get the distance. However, now we're working with an object that is accelerating, right? Gravity is accelerating this object downward, so its speed is constantly changing. So it's more complicated. We can't just use that simple speed times time or rate times time equals distance thing. We gotta try something else, or think harder about it. And this was actually a problem that Galileo looked at and sort of figured out. But it really isn't a very easy thing to do. As it turns out, if you release an object very high up, so this longest arrow is showing 80 meters, which is some over 200 feet, 250 feet or something like that. So this is dropping an object from a very high, or pretty high building maybe, or something like that, a skyscraper, I don't know. But anyway, you release that object, and you could, if you were able to make note of how far it went each second, you would note that in 1 second it will have traveled 5 meters, about 5 meters. After the second second, it will have traveled 20 meters. After the third second, it will have gone 45 meters, and the fourth second will have gone 80 meters. So something that you'll notice is that it's going farther and further each second, which again is an indication that it's accelerating, its speed is increasing. So it's moving further and further and further. And, well, from this information and from some other stuff, Galileo was able to infer and create a mathematical formula for the distance an object travels when it accelerates. But we'll talk, before we get to that, let's look a little bit more at Galileo, what Galileo did. So as I mentioned in a past lecture, Galileo actually used these inclined planes and sort of rolled balls down inclined planes. Right? And as it turns out, if you think about the slide before, it only took 4 seconds for an object to go over 250 feet. Right? So if I just drop an object from, say, 6 feet, it's going to hit the ground in probably less than a second. So the issue for Galileo was essentially that time interval is too short to really get good, accurate data. Right? So he wanted to observe the object falling, but he didn't really have a very good way of keeping time, and especially very short times like that. Right? However, he realized that if he rolled balls along planes, along these inclined planes, these different angles, that the motion was essentially analogous. It was the same sort of motion, except for the acceleration was less overall. So it was still a constant acceleration, it's just it was less if it was moving on this plane like this. And he realized that at a very shallow angle, it would be much easier to measure the acceleration, or the time in between, or the time that it took to go certain distances. And you could actually relate that to free fall, because free fall is essentially rolling down an inclined plane that's vertical. So you don't have to worry too much about that, but essentially you can use that information from an inclined plane to extrapolate to just falling down, straight downward. And just for some historical interest, this is actually an image of one of those, apparently it's one of the inclined planes that Galileo used. I believe it's in a plane, or in a museum somewhere. And yeah, you can see it's just a sloped surface, and he had these, I think those are little bells or something, at different positions along the plane, and he used a number of things to actually try to measure time. Because if you think about it, we measure time pretty easily. We have clocks that use, well, depending what it is, it might be gears and springs, or it might even be atoms jiggling around. But back in Galileo's time, it wasn't really very accurate clock or ways to measure time. So I think he actually invented his own water clock, which used the dripping of water to keep time intervals. But he also just used his own pulse, so he'd count his heartbeats essentially, and that was another way of keeping time. So after some pretty painstaking work that Galileo did with his inclined planes, listen to his heartbeat, their timing. He was doing observations about the distance that objects were traveling under that acceleration. Right? So whether or not it was under the full acceleration of gravity, just dropping straight down, or like I said, whether you just do it on an inclined plane, so that the acceleration is still constant, but it's a little bit, it's less, so it's easier to measure those distances. So what he found was essentially that the distance that those objects were traveling was proportional to the acceleration. So that meaning that if you had a very shallow inclined plane, it was much lower acceleration that it was under, or the acceleration was much lower overall, so the distance it traveled was much less, right? So less acceleration, shorter distance that it travels in each of those time intervals. Or if you go to a much steeper inclined plane, right, much greater acceleration, a much longer distance that those the balls were rolling in each of those time intervals. So, on top of that, he also found that the distance that those balls were moving along the plane was proportional to not just to the amount of time that they had traveled, but actually to two factors of the time that they had traveled. Meaning that if essentially, if the amount of time that elapsed doubled, right, then you'd get a factor of 2 for each of these times. The distance that it traveled would quadruple. Right? Or if the amount of time tripled, the distance that would travel would be 3 times 3 would be 6 times the distance it would travel. Right? So this is what is meant by it's proportional to the time squared, or 2 factors of the amount of time that it's traveling. So essentially, he figured out both of these things, and through, I think, just some other analysis of his data, you could figure out the proportionality constant to actually create an equation that told you how far something's going to travel given the distance that it had traveled. Or sorry, given the acceleration that it was under, that it was experiencing, and the time that it traveled. So, there you go. In the end, he found out that the distance that an object that's moving under a constant acceleration is going to travel is actually equal to, right, the acceleration that it's experiencing, 2 factors of the time that it travels for, right, so the time squared, and there's this factor of 1/2, turns out. So, That's written out one way, very kind of elongated with all those things explicitly sort of stated there, but much more compactly, you might see this equation written as the d is equal to 1/2 at squared. Meaning the distance an object travels is equal to 1/2 times the acceleration the object is experiencing multiplied by the square of the time that it travels. So, just compare this to, say, that example I gave you earlier, and it wasn't just a random example. This is actually how an object falls. If you release an object, then it's going to go 5. Well, if you're clever and set something up, you could measure how far it went in each second. First second it would go 5, the second second it would go 20, third second it would have gone 45 altogether, the fourth second it would have gone 80 altogether. Right? And Galileo's equation, or this relation, will give us this output. Right? So, this is a sort of a test, you could imagine, say, of Galileo's theory here, which is that if he's correct, then that equation should tell me that an object's going to that's accelerated at 10 meters per second, right? Accelerating under Earth's gravitational pull. And if you let it fall, you let it travel in that under that acceleration for 3 seconds, we should get 45 meters. That's going to travel 45 meters, right? So put those numbers into our equation. 1/2 times that 10 meters per second times 3 seconds, and then don't forget another factor of 3 seconds, right? 2 factors that time. Multiply all that out. Indeed, this equation does tell us the object will travel 45 meters. And if you put 4 seconds into that, you get 80 meters. If you put 1 second in that, it will tell you 5 meters. Right? So after, this is, some painstaking work, I'm sure, but Galileo, through that work, through that experimentation, was able to come up with this theory of how an object moves when it's being accelerated at a constant rate. So this is sort of maybe the first big example of scientific experimentation, and the scientific process being not necessarily exactly how it worked out, but an example of giving you an idea of it in play. Okay, so just in case you don't believe me on any of that stuff, fair enough. In class, I might actually drop a ball for everyone, but we're not in class anymore. So instead, I'm going to use what I got, and I'm going to show you a video of somebody dropping a ball. And it's even nicer maybe than what I would have done, because if you take this ball, or whatever object you want really, and release it, you can watch it, and you can just watch it drop, right? Cool. Not quite as interesting, or maybe hard to observe the fact that it's accelerating, that it's increasing its speed all the time. However, if you drop a ball and you have a strobe light going, then a strobe light is just a light that's blinking on and off in constant time intervals. So what you see is essentially, you only see kind of like snapshots of that object, right? So in the video I'm going to show you, we actually do exactly that, where you see the object dropping just with that strobe light, and you actually sort of see the object. Each strobe, remember, is the same time in between each strobe, but as the object falls further and further, the distance it travels between each strobe is more and more and more. So this is showing us that the object, yes, is indeed accelerating. And if you really wanted to, then Galileo didn't have a strobe light either, and if he did, he probably would have been able to figure this out more easily. But you could actually go ahead and recalculate or refind out that formula for the distance an object travels given that sort of information. How quickly that strobe is going, and how much those balls are traveling in each of those intervals. So here he's going to drop it. They even have a nice setup of this sort of evenly spaced distances drawn on this board. So let's just go ahead and see. So in real time, it's tricky to see. I don't know if this was edited together. It's a little bit weird on the editing. But they put together this final images, which essentially is an overlay You overlay all those strobe images, and you see that after one strobe, the object fell maybe this far, right? And then after another strobe, the object fell even further in that next time interval. The following interval, it fell even further, and then even further, and then even further. So the spreading out of these distances is showing you that this object is accelerating. Right? And again, if you really wanted to, you could use this information to calculate that acceleration, or if you know that acceleration, you could figure out this distance formula if you really want. And there's another video on here we're going to show you in class because it's a little bit tricky. Take a little bit of time to explain, but it's very interesting to see that if you sync up a strobe to essentially dropping water droplets or liquid droplets, if you sync it up just right, then you actually will get it to look like those objects are just hovering in space, but they're hovering at larger and larger distances the further from the source dropping that it is. Right? So feel free to check out that video. The guy, I think, explains it pretty well too. So that's all kind of encompassed in one. Okay. So finally, this is something that you could go ahead and try on your own. Okay? So all of this information, all this stuff about acceleration and changing velocity, right, means that I should be able to predict, say, how long it will take for an object to go a certain distance. As long as I'm just dropping this object, it's accelerating under gravity, and that's all only thing that's happening to it, right? Then this equation, if I rearrange it, will be able to tell me, I could figure out how long it will take to go a certain distance, right? Essentially solving this equation for a single factor of time, it would involve multiplying by 2, dividing by acceleration, and square rooting. You don't really need to do that. I can just at least tell you for one example is if I say how long would it take for a ball to fall or an object to fall 3 meters, right? And 3 meters is 9 3/4 feet, about 9 feet and 9 inches, right? So pretty tall, but you could probably find a way to get up to about 9 foot 9 inches, about 3 meters, right? And it turns out if you solve this equation, then it will tell you, or you will find that it takes about 0.77 seconds, right? So 77 hundredths of a second. So it's still pretty quick, but you all probably have, or all should have, I think on your phones, pretty much all phones in their clock feature have a stopwatch. And if you say, maybe you might need a helper, or maybe not, you just find a way to get a ball about a little over 9.5 feet off the ground, right? 9 feet 9 inches. Try to measure it in some way if you can. And when you release the ball, start the stopwatch, and when you see it hit the ground, stop the stopwatch, right? And I would bet you money if you're accurate about when you start and when you stop, and the height, that it is actually about 9 feet 9 inches, then you're going to measure basically 0.77 seconds. Okay? So this is something you could try. You don't have to, but you might, if you're interested in figuring it out or seeing it for yourself, then there you go. Because that's the real beauty of the science here, is that we have this theory of how objects move when they're being accelerated. That theory can make predictions, and those predictions can be tested. And when you test them, if they turn out to be true, turn out to be correct, then you say it's a good theory, right? I'm going to keep going with that theory. It doesn't mean that theory is going to work everywhere, and we'll see later on that there are many cases where we have theories like Newton's theories, Newton's laws, and they work very well in a lot of cases, the cases that we normally deal with, but they actually don't really work well in other realms of physics, right? Generally speaking, in terms of things that are very, very large, or moving incredibly fast, or things that are incredibly small, right? It turns out that Newton's ideas start to break down those areas. That doesn't mean he's wrong here, where we are, because he's actually very, very accurate where we are. It just turns out it doesn't actually extend all to everywhere. So that was getting ahead of myself. We'll get to some of that stuff way later in the course. Yeah, so hopefully you try this out. It's a fun, very easy experiment. Well, I say fun. You might not think it's fun. whatever. It should be at least interesting that you can test this. That's my hope. But yeah, that's all I got for this lecture. So hope you enjoyed it, and I hope you learned something, and we'll see you later.